let me introduce you again to Mathieu Carrière. Please enjoy the talk. Thank you for being here.
All right, thank you. So I'll share my screen. And here we go. Okay, so maybe I'll put that there. Thank you for the introduction. Very pleased to give a presentation of this paper, this work that I've done with my co-authors, Mark and Theo. So they're not from the datashape team where I work on. Those are external collaborators. And this is a talk that has been accepted actually to NeurIPS. So if you're interested, you can check the paper online on archive, but it will be soon part of the proceedings. So yeah, the talk itself is called Diffeomorphic interpolation for persistence-based topological optimization. And indeed, its main focus is really about one aspect of TDA, of topological data analysis, which is related to optimization. So I guess for starters, and just to be sure that everyone's on the same page, I will do a brief recall of TDA and what are the main descriptors I'll be looking at. So TDA, topological data analysis, is this field where you try to capture geometric and topological features from datasets, okay? Using different types of descriptors. The one that I will use most, or only the one that I will focus on today, is the so-called persistence diagram, right? This is this object there, which really in itself just takes the form of a point cloud in 2D, right? Every point in this point cloud being representing, if you want, the presence and the size of a topological feature, right? Which can have different dimensions, like in dimension 0, it can be a connected component or loop or cavity, etc., etc. Okay, and just a reminder also, because I assume some of you already know about this, those persistence diagrams, they actually come from what we call filtrations of data points. Okay, so you give me a data set, and if you also give me what is called a filtration, I can get you this so-called persistence diagram. Then the whole idea of a filtration is, or the persistence diagram computation is to look at what are called the sub-level sets of the function. Okay, so the easiest is to go with an example, because I think it's very compelling. So let's say our data set is actually this one, an image of a 0. And we will use, as a filtration, we will use a function which is just the pixel value, okay, the pixel intensity. Okay, so the sub-level sets of those functions are just the subset of pixels whose function value is at most some threshold alpha, okay? And we will make this alpha increase from minus infinity to plus infinity. So in that case, I will go from alpha very bright to alpha very dark, okay? So at the beginning, if I just look at the pixels whose function value is less than, at most white, I just have those ones, okay? The brightest pixels. In terms of topology, I see two connected components. If I now increase to, let's say, grayish, one of the two connected components got attached to the first one. So, at the beginning, when I had two connected components, I started two intervals. I let the component leave. And when I reach this value, one of the two components is attached to the other one, so it dies in a way. Okay, so that creates an interval like this, representing the lifetime of the component. The other connected component is still alive, right? We still have one connected component here. Plus, I'm putting another dot in color purple because we're also creating a cycle, so a topological feature, but in another dimension. Same thing here. If I increase to now dark gray, I still have my cycle, plus I created another one, the small one here. I have three more connected components on the sides, so three new green points, until I have all the pixels in the end, and the only thing that remains, well, is again the component. All the other features are stopped. And that's how you get your persistence diagram, okay? You can use just the endpoints of every interval as the 2D coordinates of 2D points, okay? So really, this persistence diagram is an equivalent representation of this object, sometimes that we also call the persistence barcode, okay? With the interpretation that usually the longest the bar, like the longest the interval, or equivalently, the further away from the diagonal means if you have a long bar like this or points that's further away, that means that the corresponding cycle, well, has a big size, so it's likely to be relevant signal. Whereas on the other hand, what has a small size like this one, points close to the diagonal, they're likely to correspond to noise in the data. Okay, so this interpretation is not always true, but it's very often the case that close to diagonal means big noise. So it's a useful interpretation as well. All right, those are the points we usually care about. Okay, now that's being said, so these persistence diagrams, they've been used quite a lot of times, okay, for many different purposes in data science. There are like plenty of applications where they use persistence as a feature to create new descriptors on which you can train whatever data science model that you like. One application I would like to actually give more details about in this presentation is something slightly different, related to what is called regularization. Okay, and this is a typical example that comes from a paper of my colleague of 2019. Regularization is really about not really creating descriptor, but rather constraining models based on topology. And here's a reason why that could be interesting. What I'm showing here are blue and orange points, okay, so points with different labels. And in red, you have the boundary learned by a model, in order to classify the points, okay? So your model, whether it is a neural network or something else, has learned that inside the red, points should be classified, orange, +1, and outside the red boundary, it should be blue, labeled -1. But as you can tell here, there's been something called overfitting. So just because we had two outliers at that place, the model created a small island like this, like a small component of the boundary. Even though it's quite unlikely that if I generate new data, I will probably also have blue points in there, right? It's likely that those two orange are outliers. So this is really what is called overfitting. Well, this is something you can prevent because you could tell at training time that you want your model to have, for instance, if you look at its boundary in red, to not have too many connected components. Okay, some of them it's okay to have more than one, for instance here, but you want to prevent the models to create small disconnected islands like this, or to prevent it to do it too much. Okay, so this is an example where you would translate a data science question or problem into really with a topological formulation, right? Here we relate overfitting with connected components. Something else that's been used actually quite a lot, or a few times already, is dimension reduction, right? You have plenty of models nowadays, for instance, using autoencoders, who work by learning a latent space. So you start with some data in possibly high dimension and you embed it in 2 or 3 for visualization purposes. But then one thing else, something that you could ask in addition to the usual loss that the models try to minimize, whether it is the variance or the difference in distances by the different models, you could also impose that the latent space in 2D has the same topology, okay, so in terms of persistence diagram, than the original space, okay? And this is an example here where my original space is, well, just 2 circle intricated. I'm drawing them in R3, but the original dataset is in R9, okay? If I apply a data set, well, for instance, an autoencoder, I get a 2D visualization of that, okay? So I'm representing the points with just 2D coordinates. But if I further impose that I want the latent space to have more or less the same topology, you see that the model will try to reduce the amount of overlap between the circles, because in the original data set, the circles do not intersect. So based on that, the model will try to push the circles away if you constrain it by topology or by persistent homology or persistence diagrams. All right. Okay, so that's interesting. One, I guess, common feature of all of these models, of these applications, is the ability to minimize a loss or a function that is defined on a persistence diagram. Okay, or equivalently, given that many models are now optimized with gradient descent, if you think about training a neural network, the question amounts to defining what means or what is the gradient of a persistence diagram, right? If you want to minimize this function, and if you want to do it with gradient descent, that means you have to differentiate the persistence computation itself. All right, so that's, if you want, what I mean by persistence optimization, and that's the main theoretical topic of this work, the work I'm going to present. So let me just say that this question, I'm not the one, I didn't introduce the question. It's a long-standing question, actually. People have thought about defining gradient for persistent diagrams, actually, for some time, at least since 2015, okay? So there's a long line of work, more or less adapted to the different filtrations of the different data sets that people are using. This is also a topic that I've worked on in a series of papers, and today I will present like the last iteration, if you want, of that series. But if you are interested in what I will talk about today, I guess I'll also advise to take a look at the others, which really is about extending persistence optimization with diffeomorphisms. Okay, and so we'll see why it's interesting and why I mean exactly by this. But first, maybe I'll briefly recall what we obtained from those two previous, let's say, works on optimizing persistence. The simplest way you could think of defining a gradient for persistent homology is the following. Actually, it comes quite naturally as soon as you remember or get a bit into more details about how persistence is computed. Okay, so quick summary of how it goes. Most of the time, persistent homology, we compute that, not the only way, but many times we compute it practically on simplicial complexes, which are, if you want, triangulations of your data sets. Okay, we do that because simplicial complexes are, if you want, a way to build well-defined mathematical spaces out of finite and discrete data sets. But you can really think of that as a triangulation in higher dimension, like a triangulation where, in addition to the usual point, edges, and triangles, you have higher dimensional bricks that you call simplices. Those bricks could be, for instance, tetrahedron, and you glue them along their faces. Okay, so if I give you a simplicial complex, right, now persistent homology goes with a filtration, as I described before. But if you go a bit more into details, the algorithm just processes the simplices one by one. First, it sorts them based on their filtration values. Okay, so remember, on the image, the filtration was the pixel intensity, but I can use any function I want. So here, for instance, I'm just filtering a simple triangle based on the filtration values on all of its simplices, so 3 points, 3 edges, a triangle in the middle. And the algorithm just works because we know that every time we add a new simplex in the filtration, either it creates something or it destroys something. Okay, so for instance, at the beginning, the first simplices to be inserted are the 3 dots. Each of them creates a 0-dimensional cycle. Then I'm inserting the edges. The first 2 edges destroy the connected components because it attached them to the first one. The last edge creates something because it creates the cycle made of the 3 edges. Yeah. And the triangle is negative. It destroys, it fills in the triangle, the cycle. But the message of this is that then it's an easy fact. Based on that, it's easy to see that in a persistence diagram, the points, if you want, it's almost tautological. Every point in a persistence diagram is always the filtration value of some positive and some negative simplex. Okay, so then those, you call them usually the critical simplices, and then you're almost done, right? Because then the gradient, if you want, of a persistence diagram point with respect, for instance, to the filtration will just be the gradient of the filtration itself applied on the corresponding critical simplices. Okay, so here's an easy example. If you're given a point cloud and you want to optimize its so-called RIPS filtration, so the RIPS filtration in that case is obtained by looking at spheres, you see increasing around the points, and you're going to create simplices between the points if all the corresponding pairwise sphere intersect. Okay, so this is kind of a geometric filtration that you can always apply in a point cloud. And it's an important one in the sense that this is the one that I will actually focus a lot about in the next slides. So basically, this filtration works by filtering the complete simplicial complex that you can form out of the point cloud. And you will assign a filtration value on every simplex, like for instance, this triangle, as the max of all pairwise distances between the points in the triangle. Okay, so I will compute the distance between those 2 points, those 2 points, those 2 points. I'll take the max of those 3 distances, maximum. That will give me the filtration value of that triangle. Okay, so in the end, this is what the persistence barcode looks like. And as you can guess, it encodes the geometric features of the point cloud. Like we have one long bar in dimension 0, representing the connected component, plus one long bar, 2 bars in dimension 1, representing this little cycle here and this other one here. Okay, all right. But then again, and this is the definition, right? For any simplex, we look at the max of the pairwise distances. Again, what I'm interested in here is the gradient of that. Okay, and let's say the gradient, for instance, with respect to the position of the points, the different xi's. I want to understand what's the gradient, the partial derivative of these objects with respect to the xi's, to the coordinates of the point in the point cloud. So based on that, again, I use the fact that I described before. Every point or every bar in this barcode is given by the filtration value, so this equation, applied on some critical simplices. So those critical simplices in that case are given by some points, okay, some subsets of points. And again, then based on that, I'm almost done. The only thing I need to do then is to, in these subsets, in the positive and negative simplices, identify the pair of points that achieve the maximum. So I'm denoting them with an I star and a J star. And then the gradient of the filtration value based on the position of the point clouds on the coordinates are just the partial derivative of this distance with respect to the xi. So it's super easy to compute. Obviously, the partial derivative of this distance with respect to an xi is 0 if I'm computing the derivative with respect to some I that is neither I star 1 or I star 2. And if I is one of the two, then it's basic linear algebra. We have an explicit formula for the gradient. You see? So, and this is a trivial example, well, a simple example, but for more complicated filtration, you can, for instance, parameterize the space or the different filtrations you'd like to study with a network and let, for instance, backpropagation do the job for you if you don't want to compute the gradient all the time by hand. But you see that in the end, it always amounts to just identifying the critical simplices and just applying the gradients directly on those. Okay, maybe one last, a few small details. Usually when you want to optimize persistence, you don't want any loss. You want at least a loss that is invariant to permutation, because you don't want your loss to depend on the order of the points in the persistence diagram. Okay, so if it is continuous and invariant to permutation, you can call it a function of persistence. And among the most common ones are, for instance, the total persistence, which is, if you want, for those of you who know, this is more or less sorry, like the total variation, but for the topological descriptors, or the diagram distance to a target. Like you have applications where what you want to do is force your persistence diagram of your model to match a prescribed persistence diagram that you give to the model. That could be used, for instance, in enforcing the number of the number and sizes of components or cycles or whatever. Okay, so this is something you encounter often also in applications. And yeah, easy example or funny example, toy example of the RIPS filtration I was describing above. Assume you want to optimize the position of those points so that, for instance, so that the number of holes or one-dimensional cycles is maximized. Then you can apply as a loss the opposite of the distance of the points to the diagonal, because if you minimize this, that means you will push the points away from the diagonal. Okay, and I'll skip this. If you add another penalty forcing the points to stay within the unit square, this is eventually what you get. So you have moved the points around so that their places tend to form cycles. Okay, the locations form cycle in the point cloud. Okay, so if you want this was the topic of more or less this and small variations of this were the topics of the first articles that I mentioned in the introduction. And what I want to focus on now is the subject of the other recent paper that we, the diffeomorphic interpolation, which deals with two facts, two problems, if you want, associated to this scheme that I was showing, that I will call the vanilla gradient descent, where you just use the critical simplices. The problem is that gradient descent based on this tend to be usually sparse and unstable. So what I mean by sparse is that for one given point in the persistence diagram, you have at most, well, you have two critical simplices. And in the case of the RIPS filtration, this means that you will update at most 4 different points. Okay, the 2 points achieving the distance in the positive critical simplex and the 2 points achieving the distance in the negative simplex. So this is what we mean by sparse. If you use vanilla, you update only a few points at every iteration. And now it's also unstable, which in turn means that the gradient descent is oscillating a lot, very erratic. And this is because the location of the critical points here is itself unstable. So if, let's say I have my point cloud, okay, I optimize it. This means that I update 4 points, okay, the critical points. But then after I update this, the critical point will change because I've changed the filtration. And they are very unstable in the sense that the new critical points can be very far away from the other ones, the ones that I had before. This is what I mean by instability, and this in turn often lead to losses that are super erratic like this and hard to minimize. Here, in that situation, I just wanted to actually optimize this point cloud so that it doesn't show any one-dimensional topology. Okay, what I had at the beginning was points sampled on a circle, and nothing in the middle, and I wanted to decrease, to minimize the total depth, so basically to get rid of that point in the circle by pushing some points towards the center, basically. But again, based on those two facts, the gradient descent is super not efficient. This is something that I can show also with this little animation. Okay, so this is my initial point cloud, and as I optimize it, you can tell that the arrows go everywhere at very different places at every iteration, and because of that, gradient iteration is super slow. Okay, and very, very erratic. Okay, so how to fix this? And you see, the idea we propose in that recent work is really not complicated, actually. It's just then let's extend this to a diffeomorphism, or if you want, to a vector field. Okay, let's try to find a smooth vector field, which in that case would be defined on the whole space, not only on the critical simplices. Okay. Obviously, I don't want any vector field. I want one that coincides with my gradient on the critical points. Okay. So everywhere that my gradient is non-zero, I want the gradient to be the same as the vector field. But on the rest of the vector field, okay, I'm free. I just want this constraint. Okay. This is actually a topic called diffeomorphic interpolation, and maybe some of you know that already from shape analysis. It's been used in very, very different contexts. Notice though that in its way the problem is ill-defined, because obviously if my only constraint is to match the gradient on the critical points, then there are many solutions that could work. Okay, so there's a way to make the solution unique, is to look for, again, a diffeomorphism, but to try to find the one, for instance, with the smallest norm. Okay, so you can assign a norm to vector spaces, okay, by embedding them in specific Hilbert spaces, and try to find one that minimizes, well, its norm. So if you want this kind of minimization of the norm ensures also that your vector field doesn't, do crazy updates outside of the gradient. Okay, because actually you still want a vector field that's smooth, but you don't want a vector field that's ideally you want something with a bounded Lipschitz constant or something like this, so that the norm is not so large. Okay, in that case, you can, frame this problem. You can study this problem in the so-called RKHSs, in specific Hilbert spaces that are called reproducing kernel Hilbert spaces. And in those particular spaces, there is not a closed form solution, but you can prove that the solution, the vector field solution, is of this form, okay, of this template, has to follow this template definition, a template equation. For those of you who know it, this is sometimes called the representer theorem, where here the alpha are just scalar values, they're just coefficients, more or less. Well, vectors in that case, actually, but they're just coefficients for now. And the k here, k is a matrix. And usually one of is a matrix. It's left on as a choice for the user, like what matrix to use here, little k, or kernel. We often refer to them as kernels. If you have no idea what to use, the standard choice most of the time is the Gaussian kernel. Okay, so if you give me 2 points, I will compute the distance between them, and I will compute now the identity matrix with a Gaussian function on the diagonal. Okay, this is like a very standard choice. And now that you've defined a kernel, you can obtain, you can solve for the coefficients. Basically, you can plug in the formula here, oops, within the constraints, okay, and the norm, and obtain the coefficients just by this equation. Okay, you invert basically the kernel matrix, and you multiply that on the gradient. Remember, the gradient is your input. You want to find a vector field that coincides with the gradient. So here's how you can get your coefficient and eventually your vector field. Really, you can interpret this as taking the gradient, the original sparse gradient, and just convoluting with a Gaussian kernel in order so that it's defined everywhere on space. And you can see this as a constraint on the weights of those convolutions, so that you ensure that you match with the gradient at the critical locations. All right, okay. So here's the good thing about this. Now you have a data set or an update. You see that is much less sparse than what we had before. Instead of moving at most 4 points at the same time, well, based on the bandwidth of the kernel, we can extend more points, right? We can apply the changes to the points, let's say, that are around, also, not only on the critical points. And this smoothing of the gradient has a really, at least an evident qualitative effect. So if I look again now at the same problem I was looking before, I have my loop and I want to destroy the loop. But now, in addition to the critical, well, I'm extending the gradient with a diffeomorphism. So you see that now I have much more arrows than before. Plus, if I start optimizing, I see the convergence looks really different. Now I'm really pushing moving the space by applying some sort of force or topological force or vector field, so that the loop is really shrunk in a smooth way into something with no loop inside. Okay. Right, and obviously you can tell from the loss that the convergence happens much faster. It's still a bit erratic, but the size, the amplitude of the oscillations is also more controlled. Actually, you can even quantify the Lipschitz constant of the diffeomorphism in that following sense. If you look at two neighboring points in your input point cloud, well, you know that the difference in the vectors that you apply on them will be basically dependent on the condition number of the kernel. This term here is there because you know that inverting large matrices can sometimes introduce numerical errors. So this is the related terms. If your matrix is hard to invert, the resulting gradient can oscillate more. So the Lipschitz constant can be bigger. And it also depends, well, on the dimension, on the bandwidth of the kernel, and on the total persistence of the persistence diagram, right? So again, the total persistence here is the one that I described, I think, earlier. Yeah, this one, total persistence, the sum of the distances to the diagonal. All right, moreover, you can also show that in that case, this is what I meant when I said a topological force. If you extend the gradient descent with this diffeomorphism, then you can more or less see the gradient descent process as an approximation of this ordinary differential equation, where the derivative of the points are given by a flow, by the diffeomorphism that you learn from the gradient descent, or from the gradient on the critical simplices, applied on the point cloud. Okay. So it has, now let's see a few good, and I will, I guess, yeah. I will end with some nice applications of this gradient extension with diffeomorphism. The first one is related to subsampling. The main motivation is that it's known in the field that computing a persistence diagram is actually difficult. It's cubic in the number of simplices, actually, more or less. So obviously, if you have, I don't know, like a million points, computing the whole RIPS persistence diagram will be super expensive. So people have obviously thought about workarounds, and one of them is to just pick a subsample, okay, and compute the persistence of the subsample. What's nice about diffeomorphism is that we can do the same, compute a subsample, but then extend the gradient on the subsample to the whole space, okay, instead of just moving the critical points of the subsample. So if you want, if you match the two, okay, so, well, this is the exact same example I was showing before, except that compared to the animation I was showing, the gradient iterations here are super fast because they're computing on a very small subsample, the red points of the circle. So given that I have a much smaller point cloud, persistence is fast. And given that I'm extending it, I'm still moving all the points at every iteration, okay? So if you want, this allows for really lightning fast or super fast, much faster than vanilla, at least, computations of optimization. Here's another example where I have a very large point cloud and I'm trying to optimize the size of the cavity inside the 3D shape. So I'm basically inflating this 3D shape. You see that actually, if I use the original gradient descent scheme, where I just pick the critical points, well, first I have to subsample because I have much too many points to compute usual persistence. But if I subsample and only apply the loss on the critical subsamples, the usual optimization doesn't do anything because I have so many points that any subsample I take is not really meaningful and not very representative. Whereas if I extend with diffeomorphism, well, gradient is not super smooth, but at least I can optimize and get to something. So again, in black here, you have what the point cloud looks like after 1,000 iteration. Obviously, vanilla made no difference. Whereas with diffeomorphism, well, yeah, obviously we did optimize something, and again, in a smooth way. Something a bit maybe less toy-ish is this dimension reduction I was describing at the beginning of the talk, where I was trying to learn latent spaces and to make them follow in terms of topology. I was trying to constrain them to have the same topology than the original space. Then we can go back to that example. Maybe I'll start with the image because it will be easier like that. So this is a classic autoencoder network where you have some data in high dimensional space. You let it go through an encoder. Okay, so now you have 2D coordinates, and then you decode it to get another point cloud of the original dimension of the space. And usually this model is learned by looking at the difference between this original point cloud and the reconstruction. Okay, you minimize the difference between what you reconstruct and what's the input. Okay, and you use what's in the middle as a latent space. So an issue, if you want, with this, or let's put it otherwise, let's say you have, well, you know that your dataset should follow a circular structure. Okay, I don't know, maybe you have some periodic data, so you want to make sure that the latent space looks like a circle. So in that case, you can apply the usual topological optimization on the latent space, okay, to get a latent space that looks like a circle. But if you stop there, you're kind of you're stuck in a way, because now if I give you a new data point, okay, let's say I have optimized my point cloud, I have this final optimized point cloud, but now I give you a new data instance that's being generated somehow. Okay, the problem is that I don't know exactly where it will land there, because the sequence of gradient updates that I applied on the latent space to get to this optimal representation, well, they won't apply on my new point, right? Because again, remember those blue arrows that I obtained from vanilla topological optimization, they are only defined on the critical points. So generically, with high probability, if I have a new point, this new point will not land exactly on a critical point. So if I apply the sequence of gradients, well, my point will not move. Okay, it will stay where it was at the beginning. Okay, so I cannot actually push it along the circle. So that's an issue. But if you use diffeomorphism, as I was explaining, now given that I have a gradient update that's defined everywhere on space, it will also be defined on my newly generated point. Okay, so now if I follow my sequence of diffeomorphism, I will slowly or progressively push my new data point to where it should be on the circle. And that's interesting because once this sequence of diffeomorphism are known, I can push any new points to the optimized latent space in a linear time, basically. Whereas if I really wanted to push this guy here on the circle using vanilla gradient descent, I would have to recompute everything to redo the optimization from scratch. Okay. Another nice thing is that now I can also sample a point directly on the circular space, follow the inverse of the diffeomorphism to push it back to where it should be on the latent space learned by the encoder, and then decode it somewhere. Okay, which means you can really provide me a black box autoencoder. Okay, I don't have to modify the parameters of the encoder and still modify the latent space. Okay, you can give me an encoder that has been trained somehow in a specific way. I can fix the latent space with topological optimization and still plug and then work on this optimized latent space, sample new data in this latent space, and then follow the gradient back, and then apply it on the decoder to get newly generated points. Okay, and this is, I guess, an illustration of that. I have a data set given by rotating images. See that this is the same object, but taken along different angles. In orange, you have what a neural network has learned. Okay, so it's obviously a curve in the latent space, but doesn't look like a circle. I can force this to be a circle with topological optimization. Okay, and now the advantage of this is that if I have a circle, I have a natural parameterization with angles. So now I can just specify an angle, so specify a blue point, then push it back to the latent space learned by the network, okay, and decode based on that. Okay, so the advantage again on this is that if I want to generate new data with a variational autoencoder, I can basically sample on the optimized latent space and then get new data without having to touch or to relearn the model. Okay, and again, this is something you cannot do with vanilla gradient descent. Okay, and here in that case, yeah, I forgot to say, but it works because at least here in this example, we have a prior. We know that the latent space should be a circle because we know the pictures are of the same object and are parameterized by an angle. Okay, we have other examples in the paper on biological examples, for instance, where we're taking cells taken at different phases of the cell cycle. So again, this is a strong prior for having a circular latent space, and on which we can play the same game. Generate new data without having to touch the model again, just using it as a black box, but by optimizing the latent space of the model. Okay, right. Okay, so that's more or less all I wanted to talk about today. Many questions remain open, obviously, like what bandwidth or what kernel should I use, or could I adapt them automatically based on the point cloud instead of having to fix it beforehand? Can we compute, I don't know, like the speed of convergence of this sequence of diffeomorphism? Can we even extend it to persistent homology with more than just one filtration? Many questions remains open that we left for future work. But if you want to, get a try and play with this, all of that is available in some notebooks, either in notebooks in the Goody library for the vanilla gradient descent, or in this repository for new repository for this specific diffeomorphic optimization. All right, so with that being said, thank you very much for your attention, and I'll be happy to take questions if you have some. Thank you.
Okay, so if you have any question, please raise your hands.
Okay, hello. I have a question.
Yes.
I don't know if I can put my camera. I don't think so. I have problem with
Okay, no problem.
So thank you very much for your talk. It's really, really nice. We are working in almost similar problems.
Okay.
I have some questions for you. So one of them is, so you use, in this explanation, you talk about iterative filtration, but I assume that you can use any filtration. Yes, but the thing is
sorry. Sorry. This is actually a very good point, actually, that I didn't emphasize, and you're right to ask. I mostly spoke about this Vietore strips also because eventually what I want to do, is extend the gradient, but that only makes sense, or for now, it makes the most sense when you have a filtration on a point cloud, like a Vietore strips or alpha filtration or XESH. But if you give me something that's different than a point cloud with an arbitrary filtration function, I guess we can extend or develop a similar strategy, like extending gradient like that with a diffeomorphism. But then we need to figure out what a vector field or what a smooth vector field means if my data is not a point cloud, So this is, if you want, in the way I presented it, it's really associated to RIPs and filtrations like this one. And even though we could extend it, it's a bit less natural or less intuitive what a diffeomorphism would represent.
And you need to have to add one simplex per time for your computation. So this is compulsory, or can you add several simplex, making some adjustment or not?
So, okay, I guess you refer to this step where I was saying that we insert them one by one. So the simplices, they can have the same filtration values actually. Like here, I could have also had 5.2, like the same values here.
Okay.
But the only thing when that happens is that you still have to break it into an arbitrary order. You still have to decide whether you want this one first or this one first.
Okay.
The good news is that the resulting persistence diagram will not depend on that, on the order that you fix. But actually, practically speaking, you still have to decide which of the two you want to include first. It doesn't impact the result, but in practice, you have to fix an order. Yeah.
And for this, you say that the computation is cubic time, but
yes,
there is like a common say that it's linear in practice.
True.
So
this is totally right.
Instead of computing the persistent homology of all the point clouds, you use a subset, and then you extend the graph. This is your idea. But how do you choose? How do you choose this subset? Do you randomly, or it is better to use some topological well spaces points? I don't know. How do you choose?
This is a very good question, actually. In this experiment, we did. Let me remember that I'm sure I don't say something wrong. I think we did it randomly. So every point has the equal probability of being picked, and we sampled with without replacement among the point cloud. Although this is probably suboptimal, I guess you could probably get better speeds or some more theoretical insights if you were to use other better sampling strategies. For instance, using furthest what's it called point sampling, where you first pick a point at random, then you take the one that's the furthest away, you pick this one, then you take the one that's the furthest away from the previous two and you pick this one, etc., etc. I guess that would guarantee at least, or that would prevent you from, if you're unlucky, sampling, too many points in a region and not enough elsewhere. But we didn't study that very much, so that's.
So it is good. Sorry. So
go ahead.
It is good that the points are like representative of the whole data set, right, or not?
Yes, for sure, definitely. If you can guarantee that your subsample is not so different from the original sample, if you want, that you have enough representative, that's obviously going to be beneficial. Yeah, definitely.
Okay. Because this is very good, because we have a kind of obtain a representative data set with very close topology, persistent homology topology regarding the whole data set. Maybe applying this representative data set could be good for your approach.
You mean you have a way to find a good subsample on which you can prove that the persistence is close to the original one?
Yeah.
Okay.
So maybe
good to take. For instance, it would be a perfect candidate for this. Definitely.
Yeah. Okay, another question. Sorry, this is the last one. So you say in one of the last application that if you know that the latent topology is bad, then you can correct the
right. Oh yeah, right here, there. Yeah.
So how do you compare? How do you know? How do you check that the latent topology is bad? Do you compute the bottom distance or what?
I see. So right now we did things a bit qualitatively. So basically, we were expecting to have a circle based on the data. So by eye, we checked that it looked like a closed curve, but it wasn't circular. Something that we measured with also the persistence itself of the orange point cloud. Because if you compute the ribs of this, you will see that you have two loops, one here and one here. So this is a way to, if you want, check that it's not satisfying. And then we corrected. Yeah. But in most of our experiments, we assumed that the data had to be circular. So when this is a prior assumption, prior knowledge, just based on the data. Then we confirmed that the latent space, the original one, wasn't so great based on persistence again. And then we fixed it, the way I described.
Okay, because if you go to the slide with the how
the one before.
This one, then
this
the
one,
encoder and the decoder, at the end of the day, they are functions, right? They are functions.
Yeah. Yes.
So one thing that we could apply there to compare the topology is the partial matching that so I see here another application of our work, because we compute the topology of the image of the function. Okay, so this is the latent space induced by the topology of the domain. So maybe
I see.
Have a quantitative measure of to see if
like it would be, if I understand what you're saying, that would be a great measure. So by basically measuring the topology induced by the topology of the original space, you have a good way of quantifying whether you have correspondence or not. So that's a very good criterion, actually. And that this same thing than the subsampling strategy, it could very well fit in there, or we could make a very good use of it because we could automatically detect with this if the model itself has an issue or not. Because in our experiment, we assumed that the model had an issue, but we could actually measure it with your criterion.
So it's very a lot of things that I think we can collaborate. So I'm very happy.
I mean, I would be super interested in looking at the if you have drafts or papers, I would love to look at this.
Okay. So thank you very much again.
Sure. Thank you for your questions.
I have a question. Many thanks for the talk, Mathieu. It was super interesting. I had seen some articles on this topic, but your talk was very clear, and so thank you.
Okay,
and
sure. Thank you.
And the idea of the diffeomorphism, it makes so much sense. So I have it's just basic question, but okay. So imagine you have a data set and you get this some autoencoder, and it maps all these features, and then you optimize them. Then imagine you get a few circles. How do you know which ones are important and which not? Or like, is there some? Do you have some ideas on that?
For deciding which one of the circles is important, for instance?
Yeah, to have an idea of how is your data set. Like, I don't know if you are looking at this, the one of the DAX, but imagine you have other figures as well, and you just put all of them.
Right. You mean maybe I have other figures of the other objects also rotating?
Yeah.
And you want to decide which ones is that it? Which ones you want to optimize, or?
Well, you have your autoencoder, and then maybe you optimize to get more cycles, and you see a few cycles in the output. So the question is, which ones are more important or not? I don't know if the question makes sense.
Okay. I think I see what you mean. Actually, for this, we don't have, for now, we don't really have a way to decide or to answer this. I guess for now, we're really proceeding with, I guess, qualitatively, in the sense that, you know, we optimize, we see some circles, and then in order to decide whether this is good or not, or what circles should we actually focus on, for now, we're just basically look at what are the associated data points, basically. And so it's a data-driven thing in a way, which is also a bit, you know, not super satisfying, because ideally you would like to do that automatically. I guess one thing, but maybe one way could be actually the criterion that we just discussed. You could kind of compare the circles that you get in the end with what is, you know, inside the original data set with the induced topology, and check based on that which parts you should focus on more. But for now, at least, we're really doing things a bit manually in terms of interpretation. A lot of work for improvement.
No, because I think this is a good direction for like the manifold hypothesis. No, when you know your data has some shape and you're trying to find out, no, to see if you can.
Definitely, yes.
Anyway, that was just many thanks.
Okay, thank you.
Okay, is there any other questions in here? In that case, I would like to ask a last question.
Yes.
Because you have explained the application of an autoencoder in the latent space. Do you have any plans on future applications for this edition of datasets?
Right, actually. So one of the things we would like to focus on a bit more right now is another type of model. So not really about, let's say, not really about, autoencoder models, but for those of you who know, there is this other models that approximate partial differential, ordinary differential equations. They're called the neural ODE. And this, I think, this is another application we're digging because of this observation there. Given that we can interpret this diffeomorphism as a flow, we're trying to see how we can now regularize a whole dynamic given by an ordinary differential equation. So say we want to see if we can constrain the flow of some ordinary differential equation, again with some topological constraint, this time by injecting a new potential, a new force, call it what you want, but a new small update based on topology, and to basically make the neural network learn a differential equation with some terms incorporating topology. So this is kind of the next application we're digging right now. In addition to the theoretical questions that I listed in the end, sorry, those ones.
Yes.
That we're also currently investigating a bit, but yeah. So it's, if you want, the next big ticket question.
Okay, thank you so much for your answer. So if there are no more questions, please thanks Mathieu for his talk.
Thank you for the invitation.
Thank you.
Okay, so thank you so much for being here. I'm going to close the recording.
Right. Yep.
Okay. Thank you very much. Bye bye. I have another meeting.